Okay, so now I want to look at this example of what turns out to be a vector space. This is a really important example for historical reasons. So V is going to be the set of positive real numbers. By the way, 0 is not positive. You have to be bigger than 0 to be positive. The addition operation on this set is going to be the usual multiplication. So in this setup, right, so 5 vector space addition 4 is equal to 20, right, just as an example. And the scalar multiplication in this setup is going to be normal exponentiation. So for the vector space scalar multiplication, 3 vector space scalar multiplication 2 is going to be 8. So those are the definitions of these two operations, and we claim that with those definitions, the set V forms a vector space. Okay, so if we look at axiom 2, that just says normal multiplication is commutative. This just says normal multiplication is associative. Now I've mentioned that 0 isn't in the vector space because 0 isn't positive, but we're looking for an object that does this. Right? So the object that does that is the real number 1. 1 vector space addition u means 1 normal multiplication by the real number u, which is u, which is what this is saying should happen when you have a 0 object. That means the real number 1, which is in this set, is the 0 object. Okay? And for axiom 5, the negative is going to be the reciprocal. If you have a positive real number, it has a reciprocal. And if you vector space add u to its reciprocal, then you get the 0 object, which is the number 1. Okay, so that's how this plays out. The more interesting axioms are axioms 6 through 10, so let's look at those next. And actually, axiom 6 isn't that interesting. It just says that when you take a real number and raise it to the power of k, if your real number was a positive real number, and k is any scalar, so any real number whatsoever, you end up with a positive real number. So let's just test that. If u is a positive real number like 0.5, and we multiply by any scalar like negative 100, this is vector space scalar multiplication, then we're looking at 0.5 to the power of negative 100, and we want to know if that's a positive real number, and it is. Okay, so axiom 6 is not that interesting, so let me just move that away. Right, it's just saying that if you do these operations, you stay inside of your set. And I would actually say axiom 10 isn't that interesting either. If you have the real number u and you raise it to the power of 1, you end up back with the same real number u again. So axioms 6 and 10 are not that interesting. It's really axioms 7 through 9 that are interesting. So we're going to look at axioms 7 through 9. They are all satisfied. And the way we're going to prove that they're satisfied is to understand the left-hand side and then understand the right-hand side separately and then see if they're the same. And then we'll do that for the other axioms as well. So here goes. This means usual multiplication. So there's the usual multiplication of u and v. And this means exponentiation. So we're looking at this. That's what the left-hand side of axiom 7 gives us. Now we'll compare that to the right-hand side and see if we get the same thing. Here we're doing exponentiation, u to the power of k. And here we're doing exponentiation, v to the power of k. And we haven't done the vector space addition yet, so we'll do that next. But that's just multiplication. And we want to know if the left-hand side is the same thing as the right-hand side. And it is. That's a property of real numbers at this point. We translate what axiom 7 means with its strange definition of addition and scalar multiplication. We translate that into something that we understand with real numbers, and it turns out to be a familiar property with real numbers. Axiom 7 is correct. So now on to axiom 8. The left-hand side of axiom 8 has, in brackets, a scalar. Right? So the plus in that bracket is the usual real number addition. It's not the vector space addition. The real number, k plus m, is scalar multiplied by the vector u, which means the real number u is raised to the exponent k plus m. So that's the left-hand side of axiom 8 for this definition of plus and scalar multiplication. For the right-hand side, we're looking at u to the k we're looking at u to the m, then we're vector space adding them together, which means normal multiplication. And we want to know if this product is the same as that product. And of course they are. Right? So u to the k plus m is of course u to the k times u to the m. Let me make my m a little neater. But these are for sure equal. So that means the right-hand side is the same as the left-hand side, which means that axiom 8 is satisfied for this definition. And not only is it satisfied, but it's a very familiar property relating exponentiation with multiplication. Okay, and for axiom 9, the left-hand side requires that we do two scalar multiplications. The thing in the bracket is u to the power of m. That needs to be scalar multiplied by k, which means we have u to the power of m, and that gets raised to the power of k. That's the interpretation of the left-hand side. The right-hand side requires that we real number multiply the k and the m first, then scalar multiply by u, which means we have this. And we want to know if these two expressions are equal. And of course they are. And this is an important property of exponentiation. So now we have that the axioms are satisfied. So why is this important? Well, for hundreds of years, before we had computers, but needed to develop mathematics to get to the point where we could invent computers, we had to calculate really hard things, and we did it with logarithm tables. The idea, discovered by Napier hundreds of years ago, that multiplication was essentially addition if you had logarithm tables, allowed for these calculations. Napier's discovery was as difficult for him then as this discovery, that this is a vector space, is for us now. The fact that V is a vector space was the key to the development of human civilization.